Start off by thanking Greg and Christina for inviting me and allowing me to introduce our new PRISM mission to the Gruithuisen domes to you today. Okay, there we go. Okay, so our Lunar-VISE investigation, which is using a suite of instruments both on the lander and a rover, is really driven by two main goals. The first is to understand how lunar silicic volcanism works, as typified by what we see at the Gruithuisen domes, but also to understand the geotechnical properties of the lunar regolith on those domes. Our plan is to launch and have surface operations in mid-2026 with a nominal 10-day mission. Now, on our lander, we have a suite of cameras. All of those will be provided by Ball Aerospace. Our descent camera will actually be imaging the surface as the lander is making its way to the surface and imaging how the lander interacts with the surface regolith. We also have context cameras that are on the lander, and those will be used to provide geologic context of the landing site, allow us to plan our rover traverses, and also be able to map the regolith properties around the landing site. Now, on our rover, we have a suite of 3 instruments. And the first is a multispectral visible and near-infrared camera. And that camera is going to be used to map variations in composition and morphologies at really high spatial resolutions. And this camera is very similar to the Ball context camera that they will be providing. The only difference is that we're going to have spectral filters that will give us that multispectral capabilities. In addition to the multispectral visible and near-infrared camera, we'll also be having a multispectral thermal infrared camera, and this is the LV-Cirrus, and this is based on Ball Aerospace's L-Cirrus radiometer that is going to go to the south pole of the moon as part of CLPS Task Order 19C. We're going to use LV-Cirrus to map variations in composition and thermophysical properties of the rocks and regolith at these centimeter scales as we traverse the dome. And finally, or last but not least, we will also have a gamma ray and neutron spectrometer. The gamma ray and neutron spectrometer is going to be used to map abundances of major and key elements, including silicon, magnesium, iron, thorium, possibly some rare earth elements, and if in high enough abundance, hydrogen. And the gamma ray and neutron spectrometer is being built by Arizona State University, and it draws upon from the heritage of the mini neutron spectrometer that's going to fly as part of Luna HMAP on Artemis 1 mission. Now, our 2 multispectral cameras, LV-VIC and LV-Cirrus, will sit on top of the lander in a single enclosure. And if we assume that our rover is about 1 meter in height, then our cameras will be able to see out in front of us at about 3.6 meters in distance. And at that distance, we should be able to get sub-centimeter spatial resolution from all of our instruments. Our field of view of both cameras will allow us to see from that distance at 3.6 meters in front of the rover, all the way up to just above the horizon. And just to give you some sense of what our spatial resolutions will be like further away from the rover, if we're looking or talking about a distance of about 100 meters from the rover, LV-Cirrus will give us a spatial resolution on the order of 40 centimeters per pixel, and LV-VIC will be seeing about 2 to 5 centimeters per pixel. Now, both of these instruments that are in this single enclosure will be on a rotation stage, and this will give us the ability to make azimuthal panoramic scans. And so we'll be able to make panoramic images as we traverse the dome. And basically, as we rotate the cameras around, we'll essentially be able to image at multiple wavelengths, as we see in this image here. And then as far as where our gamma ray and neutron spectrometer will be, we will be placing it as close to the lunar surface as we can. And so it'll most likely be at the base of our rover. Now, to achieve our main science goal of understanding how lunar silicic volcanism works on the moon, we have two science objectives. The first science objective is to map local variations in composition and to correlate those compositions to rock and regolith properties, surface features, and dome morphology. And the first method that we're going to be using to map the composition of the dome is using thermal infrared observations from LV-CIRRUS to map the Christensen feature. And if we look at this spectral plot here, where we're plotting thermal infrared emissivity spectra of a range of lunar highland soils and mare soils, along with some very silica-rich materials like rhyolite and obsidian, we can see that the CF position, or this emissivity peak, shifts according to composition. And in particular, we can see that these really silicic materials have shorter CF positions, closer to 7 to 7.5 microns, whereas highlands and mare material peak at wavelengths, at longer wavelengths, closer to 8 to 8.5 microns. And so because of this, we have designed or chosen our band positions for our thermal infrared observations so that we can specifically look for these silica-rich compositions. Now, we could just use the CF position to get an idea of the silica to silica plus calcium oxide plus iron oxide plus magnesium oxide ratio. So we could use the CF position just to be able to do that. But instead, we're actually going to combine observations from the gamma ray and neutron spectrometer so we can get independent measurements of elemental abundances, which will help us better constrain the composition by combining observations across multiple parts of the electromagnetic spectrum. And we'll not only be able to map composition and get elemental abundances, but we'll also be able to use that information to determine for the first time what type of rock is composing these volcanic domes. In addition, we're going to be using the GRNS to measure thorium and also potentially some rare earth elements. And we will use those elemental abundances to help us constrain formation mechanisms for the domes. Now, as I said, it will be really critical to take what we know about composition and actually correlate that to the geology or the geologic context of where we're roving about on the dome. And so we want to take our compositions and place them into context with the rock and regolith properties, surface features, and dome morphology. And just as an example here, what I'm showing is what we're going to be doing with the other aspect of our thermal infrared instrument, which is looking at the thermal physical properties of rocks and regolith on the dome. And so using our broadband thermal infrared capabilities, we'll be estimating the porosities and thermal inertia of rock and regolith as we're traversing the dome. Now, our second science objective is to take our in situ measurements from the rover and place them in context and ground truth all of our orbital measurements. I mean, we are lucky at the moon to have a wealth of orbital data. And so we want to take what we can measure at the surface and apply that to what we're seeing in the orbital data so that we can take what we find at Gruithuisen and apply that to all the red spots or the highly silicic locations. And so to maximize our ground truth capabilities, we've chosen for the multispectral camera filters that overlap with filters that were flown on Clementine, the Kaguya multiband imager, as well as LROC's wide angle camera. And Lunar-VISE will also have thermal infrared filters that overlap other instruments, including overlap with the Diviner instrument, the Lunar Thermal Mapper on Lunar Trailblazer, and we'll also have similar bands to the L-Series instrument that will be going to the South Pole of the Moon. In addition, our rover measurements from the GRNS will also be used to place the elemental abundances in context with lunar prospector data. And so this will really help expand our investigation from the Rutizen domes across the lunar surface. Now, to achieve our exploration goal of understanding the geotechnical properties of the regolith at the domes, we're going to be using our context cameras on the lander to be able to assess the natural variations of the regolith and its physical properties around the landing site. And then we'll also be using the descent camera and the context camera on the lander to be able to see how mission operations affect local regolith properties. So we'll be watching to see how the landing interacts with the regolith and how it affects the geotechnical properties. And we'll also be seeing how the rover traversing through the regolith changes the geotechnical properties or helps constrain the geotechnical properties. Now, there are several actual locations on the Rutizen domes that would be useful or that we could achieve our science and exploration goals. When we were identifying or using criteria to pick possible landing sites, we were looking for areas that were fairly flat, boulder-free, but had boulders or surface features in the nearby that we could use the rover to traverse to. And so here are a few locations on the Gamma Dome and the Delta Dome. But in particular, if we look at this red region here, if we zoom in using LROC NAC data, we can see that if we were to land in this boulder-free area within the rover's traverse, we could easily get to this crater where there's an abundance of boulders as we can see in this NAC image. But we could also traverse to the dome's edge, which would give us the ability to look at the morphologies and study the morphology of the dome in the context of composition. And then I'd just like to introduce our great science team that we're really excited to work with that covers a wide range of lunar science expertise. But I should also note that what's not on this slide are all of the engineers and technicians and project managers that are at Ball Aerospace, Arizona State University, and LASP that are really going to be instrumental to making our mission a success as well. And so with that, I will leave my summary slide and I can take any questions you might have.
Great, thanks, Kerri. We have time for maybe one or two quick questions.
Mike Lucas, University of Notre Dame. First, congratulations.
Thank you.
And then I'd like to ask, you mentioned the possibility for detection of trace elements or REEs. And that'd be very important. So can you touch on that?
Yeah, so we have seen with the lunar prospector data that they've been able to see or use samarium and I think neodymium as rare earth elements to kind of constrain or better understand what's going on within the PKT terrain. And so we are hoping that we get high enough signal counts to be able to do a similar or to do something similar at the surface, because obviously it's the rare earth elements that are going to help us distinguish between the formation mechanisms. Those will be really important tracers for that.
Great, thanks, Kerri. We will have a discussion period at the next talk. So if you think of another question for Kerri in the meantime, there will be another chance to ask that.